Well, well, well. Imagine my surprise when I saw this new TED Ed riddle that involves snakes and ladders. In the last 2 weeks, I had a video that dealt with snakes and ladders. TED Ed, are you trying to challenge me? Are we doing that? Challenge accepted. So for the uninitiated, what I like to do is to solve problems using code. And so what I do is I'll tackle this riddle and I won't do it on my own. I'll have the computer solve it for me. Let's check it out. Also, just as a heads up, I have not seen the solution to this problem before coding this solution, so we're going to tackle this together.
You and your best friend Bill are the greatest bards in the kingdom, but maybe not the brightest. The hit song you performed at last night's fair insulted the king, and now your hours are numbered. Just before your execution, you're approached by the princess, who happens to be a big fan. She slips you a pouch containing 2 magic 6-sided dice that can land any way you wish. You have no idea how this could possibly help, but you thank her anyways. As everything goes dark, you both suddenly find yourself standing in a deep cavern before a robed figure. It turns out that Death is a connoisseur of most excellent music. He's decided to give you a chance to escape your fate by beating him at his favorite game, life-sized snakes and ladders. The cavern has 100 rooms connected by passageways, as well as, you guessed it, snakes and ladders. Each turn, one of you will roll a die, then advance that many rooms. Ending your move at the bottom of a ladder means moving up to the top, while ending on a snake's head will make you slide down to its tail. Each of you must make your way through the cavern and reach the exit in fewer turns than Death himself. Before you can think twice, your host starts casting his die, and within 6 rolls, he's reached the cavern entrance. Better get moving, he says. Oh, and by the way, once one of you uses a snake or ladder, it'll disappear and be inaccessible to the other. You have no idea how you can possibly get lucky enough to win, but then you remember your magic dice. Can you figure out a sequence of rolls that will get both of you to the exit in 5 or fewer moves each?
Okay, so this is very familiar territory. Also, I'm getting a Bill and Ted vibe. Anyone else? Okay, so what I've done here is I've just gone ahead and I've basically made a mapping of the position like 4 and then where you end up like 75. So this is similar to the video I made earlier, and I'll have it posted somewhere above me over here, where the board and the players were basically independent of each other. But here we're seeing that now the players are actually affecting one another. So here's my plan of attack. I'm going to look through all possible valid moves that get to 100 within 5 moves. I also need to account for the fact that anytime you land on a snake and ladder, it's like a divergent path of either you take the snake or ladder or you pretend like it didn't exist. I also need to, in the end, find 2 paths that do not share the same snake or ladders taken. So here's the code I wish I had. I'm going to be using a queue, so I'm going to have some like initial path. I think I'm going to use some object-oriented approach for this. So this is going to be like a path object, and I'm going to have a number of solutions. There needs to be at least 2 for sure, and they need to be unique in the sense that they don't have any like paths that cross the same snake or ladder. So while there's a queue and we don't have 2 unique solutions, so this is going to be like a function I'll have to make, then I will just pop off one of the paths. If the path is done, then we are done with a solution. We found one. Otherwise, we will have that path create the next paths. So what that looks like is each position you're in, you need to like roll a 1, 2, all the way up to 6. And you have to take into account all 6 of those paths. And then I'm just going to add those to the queue basically. Okay, so that is a code I wish I had. Let's actually make some paths. All right, so my path class is going to have some things set up. We're going to have max moves set up to 5. And the max position is 100. And I'm going to initialize it with self. And basically I have this mapping here, so I want that to be like a parameter. So the way I'm going to do it is each path will need to have its own mapping to consider, oh, what snakes and ladders are even possible. Because anytime I use a snake or ladder, I need to like delete it because I don't want it to be in the next iteration of that path. So I think when I initialize it, I should have a snake snake ladder mapping, snake ladder map. And I'm going to keep track of the moves. All right, so let's run this. Let's actually create a path. So this is going to be like the initial path. Perfect init path. It is an object at that place, which doesn't look very good. So I'm going to define a way to represent it a little bit better. Rep R. And I'm going to return a string saying, hey, this is the path. And inside of this, I want it to be a representation of the moves made. So I'm going to do like a join, that join, and I'm going to join on self.moves, of which there's nothing in the moment. So great, there's nothing in there. All right, so I want to define a way of making a move. So make a move. Okay, so we're going to take our die roll. So what we need is the previous move. So I need to take self dot. So this is the previous move equals self dot moves. Take -1 to get the last move. I should say previous like position because it's technically a position. So the new position equals, the new position is the previous position plus the die roll. Now the reason I don't want to like have a random die roll is because we're going to be iterating over all possible die rolls. So I want that to be coming in as a parameter. And here I will have to determine true new position. Check if this new position is in our mapping, our SL, our snakes and ladder map. We're going to need to create a new path. So what this looks like is the new path is going to be like kind of a copy of this, whatever the current path is, the self, whatever self path is, but it needs to have this new position because it's in the snakes and ladder mapping. We need to consider both the position at the end of the snake or ladder, as well as pretending as if it did not exist. So I need a method for copying a path. So I will define a class method. That's typically how you would do it. I'm going to call this from path. So we're going to create a new path. So this is going to be a new path. It's going to be path. And we need to set the mapping as a parameter. But what we want to do is we want to take that path's mapping, and we don't want to set it equal to each other because the mapping should be actually a different object reference. So I'm going to actually do copy. I'm going to copy it because you can take a dictionary and copy that. And that is a shallow copy. That's okay because the only things that are in there are integers. So a shallow copy should be enough. And we also need to keep track of the current moves that are there. So the new path dot moves should equal the old path's moves, but again, we don't want to copy it exactly. We want to make a shallow copy. So this is a shallow list copy. And then we just return that new path. Okay, so that's a way of creating, basically I'm just copying a path from a previous path. That's all this is doing. And so that's exactly what I want. I want a new path here, which is a copy. So I'm gonna take path dot from path, which is self in this case. And what I want to, so either way, we're going to need to remove the mapping for this, because for this new position, because this new position is in there, right? So what I need to do is keep track of what the end path is, and I need to create basically two new paths. So I'm going to need to do like the new path and like an alternate path. So I'm going to keep track of basically two different paths. So the alt position is the new path. So I'm going to do things in like one fell swoop, basically. SL map, and I'm going to pop the new position. What this is going to do is it's going to look at the new position, and it's looking at its snake and ladder mapping. It's going to pop off the new position because that position needs to be removed from the mapping regardless. And it will return the actual value associated with that. So this position is as if I would have taken the snake and ladder to its end position. But we must consider two possibilities here. The snake ladder is usable. So that would be like at this alt position. What I need here now is like an alt path, and I'm using path.from path, and the path I'm using for that is this like new path, which has had its mapping modified. We deleted that snake and ladder. It's been used essentially. So alt path.moves, we're going to append the alt position because that is the new place that you're moving to. Okay, now this is making me think even more that whenever we do the move, I would normally want to like return a single path, but because we have this like divergent logic, I think I might have the paths as like a list that just gets passed in, and we just append to that. So this is going to be a little wonky of like new paths. And I'm going to say, okay, I'm going to take our alt path that we just made and append alt path to that. Then we consider B, which is the snake or ladder was already used, in which case the position that we're in is actually just the current position. As if the snake and ladder didn't exist. So that's the new path, called new path. The moves that we want, the move we want is actually just called the new position. Basically, it's as if we didn't take the snake and ladder, and we take our, and we basically append to the new paths list that's going to be coming in. Append new path. So I'm basically adding two paths when the position is in the mapping. Otherwise, normal spot. One thing I like to do is just to check, so see if the new position is greater than the max position. I just like the idea of like setting a new position equal to that. Or actually, what's a better way of doing that? I think actually I could do like new position is equal to the min between the new position and self dot max position. And now we can create a new path here with, you know, this line of logic, path from path, and we take self there, and here we basically do kind of what we did here. Basically, this is the same logic here. We take the moves, we append that new position, and we append that to the growing list that gets put in here. Let's run this cell and see how we can take our init path and say move moves. Let's see how many moves we have. We have none. And then we say move, make move. This is our new paths, and we're going to say make move. I want to move 4. Well, hold on, where do we start moving though? This is not going to work, I think. Yeah, it's going to get an index error because there is no -1 moves. Okay, so we need to start somewhere. That makes sense because our previous position, we need to have a previous position. So let's start out at 0 here. So let's say, so we start at 0. One thing that throws me off then is our max moves. I think I'll think about that later though for now. But okay, so let's run that and see what we can do here. No, dictionary has no attribute moves. Yes, that's true. Line 15, this is true. I did something wrong here. Yeah, so the from path method, I cannot do, I should just do path dot moves because that's what we're copying. We're not copying a dictionary, we're copying just the moves as a list, right? Okay. Perfect. So new paths should have, oh no, sequence 0 expected string int not found. Oh, the join for the representation. Okay, so this is giving me an issue. Oh, because these things are numbers, right? Okay, so I need to like do like a list I need to do a list comprehension here. For number in moves, we're just going to convert that to a string real quick, and that should do that. Oh, there we go. Wow, look at that. Okay, cool. So very good. This is showing what I was talking about. So at if we're at position 0 and we go to position 4, there are two possibilities, because right now in our mapping 4 is a ladder. So if we move from position 0 to 4, then there are two possibilities. Either we take the ladder up to 75, or that ladder has already been used and you have to consider what happens if you just land on 4 and it's just like a regular spot basically. So now what we have to do is consider all possible paths. So this function here, or this method here, is doing exactly what I want. Now I need to say, okay, I want to create next paths, I think is what I want. Next paths. Okay, very good. And this is just going to iterate through all the die rolls. So first, I should not make more paths if we are at max moves. So if self.moves, or in the length of it, the length of moves is greater than self.max moves, but you have to consider the fact that we start with like a 0, because we're starting at position 0. We need to like subtract 1 from this length. So -1. And I'll just put a note here that we're starting because -1 because start at 0, starting at 0. So if we are at our max moves, then we just return an empty list basically. So this should always return a list. So actually, if you use a little notation here, you can say like, hey, this is always going to return a list. That's a little typing for you if you're familiar with that. Okay, so let's have our new paths equal a empty list. So this is what I was talking about before. So for like the die roll in range, 1 through 7 because it's not inclusive, so that's basically rolling 1 through 6. I'm going to call self.make move. Takes a die roll and new paths. So this is the die roll I was talking about, and it's going to take a list that it will update and modify. So I don't need to like return anything here. It's kind of modifying it already. I want to return the new paths from that. Okay, so let's initialize. Let's we don't need this anymore. We can say make move. No, we want to say create next paths, and it will return a list of all possibilities. Oh, this is beautiful. Okay, so you can go from 0 to 1 because you roll a 1, a 2, 3, or a 4, which there are 2 possibilities. Apparently 5 has another set here. So if I look at my snake ladder mapping, yeah, 5 is another ladder that goes up to 15. So it has 2. It's like diverging here. And so now this is exactly like touching on the logic I wish I had. So I'm going to copy my code up here and like put it down here because this is when I'm going to be using it. So I'll be able to create an initial path, right? So that's what this is. I need a .done method. Okay, that's fair. I think done is referring to the position. So define done as, so your done when the last move is the last position, basically, like this max position. Turn self.moves, the last position you're in is equal to self.max position. So when you're done, you append that path to the solutions. Perfect. And create next paths, and we extend. So actually, I think this is mostly working. The only thing that I don't have is this thing has 2 unique solutions. So I'm going to create a function here, and these are my solutions. The issue is I need to keep track of the history of which positions were originally snake and ladder positions. Right now, I do not have that. I just keep track of like the moves, but I think I also need to keep track of like which snake and ladders were used. How do I do that? So I can do that by I can keep track of that in the path object for sure. So maybe I can say SL used equals like a set. So I need to keep track of this. So this will be something that from path also needs to copy. So I need to say new path.sl used equals path.s snake ladders used is a set, so I can do another copy on that. So this is a shallow set copy, and anytime I hit a snake and ladder, which is only here, so this is like snake ladder position, then I want my alt position, because that's the one that's actually using it. So the alt path, that's the one where you're actually using it, right? Okay, so here the alt path needs to have that added. So alt path dot sl used dot add, and we're going to add the new position. New position is like the starting point, and then the alt position is like the ending point. So as long as I have a way of referencing the fact that it's been used, that's great. Okay, so let's run that again. We'll just do create paths here. So I want to keep track of this list as X just for now. X, I want to grab the third position 3 here. That's that one. And so you should have SL used, and that's a set of 4. Okay, so I know that at position 4 that snake and ladder was used. So that's all I need. I just need a set of the things, the snakes and ladders that were used by that particular path. So now that I have that, my path objects have a reference to that, so I can use that in my solutions, because I need to know what paths were actually used. Basically, I'm going to say returns true if any 2 solutions do not share same snake ladders used, I should say. If the only solution is less than 2, we're going to return false right off the bat. I'm going to look at each position of solution. So I'm going to look at all the range, and I'm going to basically like iterate through everything in front of each solution. That will go through all possible combinations. So I'm going to say for I in range, and n equals length of solutions, which is technically up here. So let's make code more efficient here. And is that, so if this is n, range of n for I, and then I need to loop through each one in front of that. So I'll say for j in range between I and n. Oh, sorry, I should make it I plus 1, because I don't want to consider, this is like the next solution. So first solution and second solution. I'll call this like first index and the second I. First set is equal to the solutions index with the first I, and I need to get the dot SL. What did I call it? I keep forgetting what I call the thing. Use snakes and ladders used, right? It makes sense. So that's a set, right? Okay, so that's the first set, and the second set is easy. Second set is from the second I. I'm going to get the snakes and ladders used for that. And these are just two sets. I want to know if the length of the first set plus the length of the second set is equal to the length of both sets combined. And so this is basically like joining the sets. So if I join the sets, that means that they don't share anything, basically. So that's all this is saying. Sets do not share any values. No overlap. We can return true right here. Just to make life easier on myself, I'm going to print found solution paths. I want to actually print the path, which is this. Print that path, just so that once I find it, I can do that. Otherwise, I got through the whole thing and nothing that was not true, so I can say false for that. I think I should be able to run this. Holy moly, I actually got some solutions. Okay, let's see. Let's go back to the picture. Okay, let's see if this thing makes sense. Okay, so so it looks like the first path went 0 to 75. So it took this big ladder. It went to 41. How is that possible? Oh, it took a snake down to 41. Okay, so it went like 1, 41, 47. So it went here. It took another snake. That's so weird. It went to 94. So how do you get to 94 from 47? Oh no. Oh wait, what? I see. It did not use this snake. It pretended as if the snake didn't exist, because if you landed on 47, you would have taken the snake. So this snake didn't, it must have been used by the other person maybe. So 47 went to 53 and went up to 94. That makes sense. And then then they just roll a 6 to get 100. Okay, so that path makes sense. It all hinges on the fact that like you're using snakes to get ahead, which is weird, and you have to have this snake right here 47 to 30 not be used. So that means that the other person, this other solution, needs to use that, and if that's not the case, then I need to go back to the drawing board. Okay, so 0 to 15, that means you landed on a 4. Sorry, you landed on a 5. You got up to 15, and then you got to 41 somehow. How do you get to 41? I see you went to 19, which brought you up to that. Okay, and then you got to 30. How do you get to 30? 30 is 1, 2, 3, 4, 5, 6. There you go. Oh, so this person used that snake, the 47 to 30 snake, and now the person at 30, then they got up to 96. How did they get to 96? They went up. They used this big ladder at 35, so they 1, 2, 3, 4, 5. Okay, yeah, they went 5. And then after 96, you just go to 100. There you go. Okay, so this is 2 solutions that all are done within 5 moves, right? 1, 2, 3, 4, 5. And that is the solution. Oh, all right, cool. So let's check out the solution on the video.
The cavern contains many routes to the exit, and it's natural to gravitate to the ladders that allow you to cover a lot of ground quickly. Like this one. On turn 2, you'd be at 75. But without any further ladder boosts, you'd need another 5 rolls to get out. Or this one. 3 ladders get you to 82. But then it would take another 4 rolls to get around the pesky snake at 88. In fact, there's no path that can get you to the exit in 5 moves using exclusively ladders.
Right.
So where does that leave you? Snakes. It's counterintuitive to make moves that take you farther away from your target, but snakes open up a surprising amount of opportunities. For instance, these 3 ladders would put you a single roll from the exit, but cost too many turns to reach by ladders. These 2 are, however, only 5 and 12 rooms from snake tails respectively. So, could you work backwards from those to find a 5-roll path? There are exactly...
Actually, now that I think about it, that idea of like working backwards, that's like a kind of dynamic programming approach. I did not think about that for this, but I think that might have been another possibility, another way of like getting to a solution.
2 5-turn routes you might find using these ladders. Ladder, snake, snake, ladder, exit. And ladder, ladder, snake, ladder, exit. So that's it, right? Unfortunately, no. The two paths share a snake and a ladder, each of which will be unusable after the first of you slides and then climbs. You won't find 5-turn moves anywhere else. So is one of you doomed? There's one more possibility to consider. The disappearing ladders and snakes can impede your progress, but could they also help it? There are two paths to the 94 ladder that almost work, except for this snake at exactly the midpoint between the two ladders. If Bill were to take that snake on his route, you could then get past it and up to the exit in just 5 moves. And good news, whichever path you choose, one of the 5 roll paths we found earlier does exactly that, without using any of your snakes or ladders. So all you need is for Bill to go first and stick to the plan. You and Bill both reach the cavern entrance and climb back into the public square to everyone's surprise. Before the guards can seize you again, you wow the crowd and King with a song about your epic contest with death. Can't wait to keep solving puzzles?
Okay, that was fun. Okay. Wow, that was a good one. You know, I had a little bit familiarity with dealing with snakes and ladders already, so I was able to kind of like tackle that without too much of a problem. But that was definitely interesting, the idea of like you needing to keep track of which snakes and ladders you've used already, because they may not exist anymore for the other person. That's actually an interesting implementation for snakes and ladders, where like one person would affect how other people can play the game. And as usual, what I love about this solution is that it's generalized. You can put in any snakes and ladder mapping that you want, and this algorithm will just solve it. All right, folks, that's it for me today. If this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time.